Albert.
There's Ernesto.
So let's
Hi,
hi everyone. Well, okay, so this is quite a new experience. So Alfredo is going to introduce me. Alfredo?
Okay. Hello, everybody. I'm Alfredo Nájera from UNAM at Oaxaca. And I'm very happy to introduce my dear colleague, Ernesto Lupercio, who is going to talk us about a very exciting new topic in math, which is Quantum Toric Geometry, introduced very recently by him, together with Katzarkov, Meersseman, and Verjovsky. So please enjoy the talk by Dr. Ernesto Lupercio from CINVESTAV, Mexico.
Thank you very much. So, well, let's start. So this is already on the archive, posted, and this will be a series of 2 or maybe 3 talks, as I am seeing the length of the subject. But they don't need to be continuous. Something that I wanted to say before I start my talk is that if any of you is interested in speaking at this seminar, just send me an email and we'll make a calendar of these IMSA talks. This is an IMSA talk sponsored by IMSA. And we will be very happy to have some of you share your work and research at this seminar. At the beginning, we have chosen this general subject of quantum toric geometry, but we are very open to all subjects in geometry and topology. Okay. Anyway, so this is already on the archive, as I said, and this is here. Okay. So let's start. So let me give the talk at a glance. Here, there is all the talk. You can see it here. And so let me describe it very briefly. So let's remember that we have the classical toric geometry. In classical toric geometry, we have this toric variety X, this toric variety X, depicted here by this kind of blobby shape. And classically, well, it is an equivariant compactification of a complex torus. I'm choosing D for the dimension of this torus in this talk. And so this is this equivariant compactification. So it has an action of the complex torus, and this action extends to the whole of X. That is the compactification. And it has a moment map because it also, this contains a real torus. And this real torus is also acting, and it happens to be the fact that this is a Kähler manifold and a symplectic manifold, and the torus acts in a Hamiltonian fashion, and so we can define this moment map. Now it turns out, well, we know that the image of the moment map is a convex set, but it turns out to be quite a bit more in this case. It's a polytope. It is a rational convex polytope. It is a rational convex polytope. And it satisfies a combinatorial condition, so it's a Del Sant polytope. In this picture, it just would only be that these are 3, because this is R3, there is 3 of these edges at every vertex. And there's this combinatorial condition. So this is the classical toric geometry. So what we're going to do in this theory, what we have done, Katzarkov, Meersseman, Verjovsky, and myself, is we have quantized the theory, deformed the theory, generalized the theory, in such a way that many of the classical statements of classical toric geometry are still valid in a non-trivial fashion, nevertheless. And so many things from classical geometry can be generalized. But now, what happens is that the so-called quantum toric manifolds depicted in this picture, that is totally analogous to this one, are non-commutative spaces. So we have generalized these classical spaces into quantum spaces, and they are non-commutative spaces. And I'll try to explain that in more detail in a minute. But anyway, whatever a non-commutative space is, and I'll try to explain what that is, our theory mimics the classical theory in that now there is a complex quantum non-commutative torus, and we have avoided a little bit the use of the word non-commutative, because of course tori are commutative groups, and they are still commutative group objects in the category of non-commutative spaces. So the commutative and non-commutative can be highly confusing. So we have decided to call them quantum. That is also a common terminology. So we have this complex quantum tori. So a complex quantum torus of dimension d, an equivariant compactification of this quantum complex torus will be a quantum toric variety. It still will be a Kähler, and it will still have a quantum Hamiltonian action. It will be a quantum integrable system, and it will have a quantum moment map. And the image of this quantum moment map will be an ordinary convex polytope. Now, not in QD, not a rational polytope, not necessarily rational. It could be an irrational polytope. On the subject of these generalizations of toric geometry to the irrational realm, well, there is several people that have worked at this. Let me just mention some names here. There's the work of Battaglia and Prato, and there is the work of Battaglia and Safran. And then there is the work of Paul Beresler and Luntz. And then there is the work of Firat Pir. And the work of, I'm running out of room. And the work of Forth. And the work of Postingel, I don't know pronunciation, and Sotil. And finally, the work of Ratiu and Zung. And I may be missing someone. There have been quite a bit of activity generalizing toric geometry from the rational realm, to the irrational realm. Our generalization is, well, not exactly the same. It's in that all of these generalizations in that we use non-commutative geometry and this kind of thing. But it's certainly related to some of this work, and the precise relations are yet to be figured out in full detail, and it's a very interesting research direction. But for now, we'll of course cover our own approach to the subject, that is using these non-commutative spaces. These non-commutative spaces. I'm destroying I meant these non-commutative spaces as models for these irrational polytopes. Now, I have to be a little bit more general than what I am saying here. I will be a little bit more general than what I am saying here, in that we don't necessarily really have a polytope. We can have just a fan. So we really have a slightly more general case than the polytopal case. But the polytopal case is exceedingly interesting, and is the one related to the classical LBM theory. Is the one related to the classical LBM theory, the polytopal case. In any case, we'll come back to all this nitty-gritty of the details. But this is the first part of the talk. Second part of the talk. Well, I'll never get to the third part of the talk, but the whole point is that once you are willing to admit these non-commutative spaces into your toolbox of ideas, then what we can produce is a beautiful modular space. We have a beautiful modular space of toric varieties. Of course, as toric varieties. Of course, toric varieties classically are way too rigid to have this modular space. But once you admit these quantum deformations of the toric varieties, then you can produce this modular space. So that we understand what's going on, more or less, the setting, let me just say that the rational points of this modular space are the classical toric varieties. The rational points of this modular space are the classical toric varieties. There is a sort of time Mueller space above this modular space. So I want you to think of the classical, very classical MGN. I want you to think of very classical MGN in your mind to compare to this situation. We have MGN, we have a modular space with two indices. G is the combinatorial type of the polytope or the combinatorial type of the fan. G is the combinatorial type that, just as in classical MGN, G is a sort of combinatorial type of the Riemann surface, and N is a number of marked points that make the modular space better. So we have this classical MGN. Well, now we have an MGN of toric modular space, but this modular space is of toric varieties. Of course, it includes the non-commutative ones. This modular space is of toric varieties, and it has, again, an index G, and it's a combinatorial index, just like the classical index G, but this index G is the combinatorics of the fan. And we have an index N. In the classical case, N was the number of marked points. In our case, is a mark gerb. It's something that we call, more technically in the paper, a calibration. And the calibration is there to make this modular space better. To make this modular space much better, we introduce the calibration. So this is more or less the talk, two talks at a glance. And the third talk, the possible third talk, is the one dedicated to the following recent theorem that we have. It's not in the paper, but I'll talk about it. And is that under adequate conditions, we can produce a nice canonical compactification of the modular space that has this amazingly beautiful topological and simplicial structure amenable to the tools of algebraic topology. So we have this, there exists this MGN compactification of the modular space of toric varieties with combinatoric G and N mark gerb, or N calibration. So again, this is the talk, the plan of the talks. But I will be very detailed because I know that this part can be mystifying for classical geometers, and because all the theory is so explicit and amenable to calculation, just as toric geometry should be, I would like to go very slowly and express with enormous detail, at the risk of being a little bit boring, well, the definitions and all that. So let me start by the main building block of all this story, that is the quantum torus. So how do we start? Well, let's start by the most basic example, and it's the following. We take R2, and we take the canonical or whatever Z2 lattice, and then we divide by that lattice, and we get a torus. If we consider this foliation of R2, and it's an exceedingly simple foliation, it's just take all parallel lines of a fixed slope that we'll call, say, H bar. So we take all parallel lines and foliate R2, and we transport via the quotient that foliation into the torus. Well, what we get is this famous and interesting Kronecker foliation. Of course, doesn't need to be on T2. It could be on higher dimensional torus, as I will explain later. But anyway, we get the Kronecker foliation, and this Kronecker foliation, it's entirely contained in the slope, or the information of this Kronecker foliation is entirely contained in the slope of this red line passing through the origin. Let me just take that one, the one that passes through the origin, make it blue, and see what happens on the side of the torus with that blue line. Well, it starts here. It starts somewhere here, and then it goes around, and it has to come back for the very first time to the transversal, to the foliation. This circle here, this vertical circle here. Well, and there is two basic cases. The rational case, when H bar is rational, and then this foliates the torus T2 into torus knots, and the quotient by this foliation is just a circle, because every leaf of this foliation is a circle, and it's just S1 cross S1 divided by S1. And this is the simplest case, apparently. And then there's the irrational case. In that case, every leaf of the foliation is dense everywhere. Every leaf of the Kronecker foliation is dense in all of T2. And therefore, the torus, the quotient of the torus by the equivalence relation established by the foliation is a non-Hausdorff space. This is the origin of the non-commutativity of this non-commutative geometry. Let me try to explain. There is a way envisioned by Alan Kohn of taking these quotients not in the category of topological spaces, but in a larger category of spaces called non-commutative spaces. The basic idea is that if we have spaces, sorry about what? Well, we can associate to them their algebras, the algebra of functions, so that these categories are the same in various settings. It could be Freche algebras, or it could be classical algebraic geometry, and this could be varieties. In any case, there is a correspondence between the category of algebras and the category of spaces. And then one could consider, well, this is inside non-commutative algebras. These are commutative algebras. So what are the spaces that should be here? And well, these are called non-commutative spaces. These are the spaces that do correspond to non-commutative algebras. In any case, there is a way to produce, for one of these bad quotients, a non-commutative algebra, so that the quotient occurs here in the category of non-commutative spaces. And in the category of non-commutative spaces, whatever that is, the quotient, this quotient, but not taken in the category of topological spaces, but in the category of non-commutative spaces, this quotient becomes a space so that it's algebra of functions here, the algebra of functions associated to the non-commutative space associated to this quotient is this not severely non-commutative algebra, it's not too non-commutative, but it's a classical non-commutative space. It's an archetypical example is xy equals e to the 2 pi I h bar yx. This algebra appears first in classical quantum mechanics, and it does describe classical quantum mechanical systems, an integral system. And here, well, this could be more general. We could take h bar complex, but in all of this work, we're taking h bar real. This is very important for us, that this h bar is real. And so from now on, think of h bar as a real number, and think that this is the algebra associated to the non-commutative torus. This is the so-called non-commutative torus, the non-commutative space whose algebra is that one. And it comes as the non-commutative quotient of the T2 divided by this equivalence relation of the Kronecker foliation. It is only truly non-commutative when h bar is irrational. When h bar is rational, it may look non-commutative, but it's something called Morita equivalent to a commutative algebra. So it's not truly non-commutative, it's just fakely non-commutative. But when H bar is irrational, this is truly non-commutative. It's a non-commutative space. Anyway, we in our paper, to make things rigorous and to be able to produce the modular space and to do everything that we said we would do, we need to enrich this commutative space a little bit. And for this kind of spaces, this is not really an enrichment. The categories are the same, but it's another way of seeing the same object. And this is the following, the so-called stacky quotient of the same foliation. So how do we do the stacky quotient of the same foliation? Well, we just take the very non-separated, but I'll explain exactly what this stack is in a minute. Quotient stack of the torus divided by this foliation. Now, there is two things we could do, and this will come back to haunt us. And we could divide by the foliation, or we could divide by the group action of R. R is acting on the torus by this flow. And so we could divide by the foliation, or we could divide by the group action. When we divide by the foliation is a non-calibrated case, and when we divide by the group action is the calibrated case. And it has to do with this mark germ that I was mentioning before. I will explain this in detail a little bit further down the road. In any case, the stacky quotient of R by this of the torus, the stacky quotient of the torus, of the real torus, by this, let's say just to fix ideas, by this group action of R. No difference if H bar is irrational, by the way. The difference comes back when H bar is rational. That's why I said that is not so true that this is the simplest case. But anyway, this T2 by this real action, if you take the stacky quotient, that's what we will call the quantum torus. Now this is a T2RH, and we have to be careful because in our notation, this is the T1RH. Let me explain this notation. Rather than taking the whole torus, it is the same to take the transversal to the foliation and divide by the rotation of angle H bar. Think about it. It is the same to take the whole torus and divide by this R action. This is this. Than to take the transversal and divide by the rotation rho of an angle H bar. These two stacks are the same. And by taking the universal cover of the transversal, this is the universal cover of the transversal, because the transversal is S1, the universal cover is R. By taking the universal cover of the transversal and lifting the image of this leaf, we get this, this red stuff gamma. But we need to add one to this subgroup. This is an additive subgroup of R. Gamma is an additive subgroup of R. And we need to add one so that when we take this quotient of R by gamma, this is the quotient of R by gamma, the stacky quotient, we get the same. So, well, just to sum it up, our torus, because this is R1, this is R1, because this is R1 modulo gamma, we will call it T1RH bar. This one, but it is the same as T2RH bar, that is this one. All these are the same stack, and it's called the quantum torus. Now, it's easy now to write the complex version. We just write C divided by 1 H bar. It's just the complexification of this one, tensoring by the complex numbers. The complexification of this one is the complex quantum torus. But observe that H bar is still real. This is important for us. So this is the complex work. And this will be the models that will allow us to do the toric geometry in the fan, as you will see. So there is no problem with going to with higher dimensions. Rather than R and gamma, we get RD, and we still have a gamma. We still have a gamma. And what is this gamma? Well, this gamma is just an additive subgroup of RD, a finitely generated additive subgroup of RD. And this gamma is what we will call a quantum lattice. It's a quantum, and this plays the role of H bar in the previous example. This gamma is a quantum lattice, and for every gamma inside RD, for every gamma inside RD, we have a real quantum torus associated to gamma and a complex quantum torus associated to the quantum lattice. We have this quantum lattice, and we have this real quantum torus associated to the quantum lattice, and this complex quantum torus associated to the quantum lattice. So let's define. This is not the real definition, it's just a heuristic definition. I will make the real definition in this talk, I promise. That's the purpose of this talk. But let me make a heuristic definition so that you see the motivation for the real technical definition. So let's make a definition of a quantum toric stack. So it is an equivariant compactification of one of these quantum torus given by a quantum lattice. So it's an equivariant compactification. So let me write an example so that you get a drift of what I am trying to convey here and what theory I'm trying to build up. So let's take h bar equals square root of 2, and the irrational case, and let's produce CP1 square root of 2. Let's produce CP1 square root of 2. So intuitively, it has to be the quantum torus that is a complex quantum torus, and then the 2 points to compactify it, 2 additional points to compactify it. So in any case, more precisely, a little bit more precisely, let me take the quantum lattice 1 h bar inside of R. This quantum lattice lives inside of R1. This is indeed R1. And this is the fan of CP1. This is the fan of CP1. The fan looks the same, except that it carries this additional gamma information. And this map is extremely important in our theory. That's why our theory is not algebraic. It will be algebraic later on in an extended sense that we have developing, and that's another large theory that is called chimeric algebraic geometry. But in this series of 2 or 3 talks, will not, because we use this function, it will be not an algebraic theory. It will be a transcendental theory. In any case, we have, remember, for a gamma, you get a quantum torus associated to that gamma. And this is C mod gamma, because gamma is inside R1. This is the complex quantum torus. This is another copy of exactly the same, and this is an automorphism. This is just an automorphism of this quantum torus. It's a perfectly good automorphism. And because we have this exponential map, we have this other way to writing the quantum torus. Is this exponential map geometrically, let me put it, it's here. It's this universal cover. So because we have this exponential map, we have this way of writing this quantum torus, this multiplicative way. This is an additive way of writing it. This is a multiplicative way of writing it. But the multiplicative way of writing it can be partially compactified. That's the whole idea. It can be partially compactified. Even if this as a topological space is highly non-Hausdorff, it's still a good stack, as I will explain. So this is the same torus, it's just an automorphism, and this is partial compactification. And now this is the upper hemisphere of this quantum P1, and this is the lower hemisphere of this quantum P1, and then we can glue them to form the quantum P1. This is the first example we have of a quantum toric stack, and it is a quantum P1. So let me, because I want to do something really more general than that, let me just speak about these quantum fans more generally. What is a quantum fan? Well, a quantum fan is just a fan, a classical fan. Now, it doesn't need to be a rational fan, but it needs to be a fan inside RD, possibly non-rational. And a quantum fan carries the information of gamma. It has a gamma. It's not only a fan, but it has as well this quantum lattice, and it has this. But I have marked these points. I have marked these points on the one skeleton of the fan. I have marked these points on the one skeleton of the fan, and I also carry that information. So in the classical case, I would take the minimum primitive generator of the rate that was rational. Now I have to mark the point. I have to mark the point to have a, and this is the Planck's length in this direction. This is a collection of Planck lengths in the quantum integrable system. But whatever it is, they are mark points on the one skeleton of the fan. Now, just as in the classical case, these fans can be rational or irrational. Well, in the classical case, they were rational. Now they could be irrational. They could be simplicial or not simplicial, just like in the classical case. They could be complete or not complete, just like in the classical case. There's a new property. They could be gamma complete or not gamma complete. And by gamma complete, we mean that gamma is exactly generated by V1 through Vp. It could be that gamma is bigger, but if V1 through Vp generate gamma, it's a kind of the nicest case, and we will call it the gamma complete case. Again, gamma could be bigger. And well, it could be polytopic or not polytopic. This is in complete analogy to the classical case, except that the polytope has to be inside of gamma for it to be polytopic. And the fan has to be associated to this polytope. So, well, this is a polytopic case. So this is the concept of a quantum fan. Now, but now I will now try to move to the actual rigorous definition of a quantum toric stack that would cover the example that I described and would be associated to a quantum fan. So quantum toric stacks are stacks, and they are stacks over A. What is A? The base category for our stacks is the category of affine toric varieties over C and toric morphisms. A is a site. What are the coverings that we take to make the category of affine toric varieties a site? Well, we just take Zariski open subsets of T. That's what we take to be coverings. And there is a bigger category that contains A, is the category of complex analytic spaces with together, complex analytic spaces, together with a holomorphic action of a complex abelian Lie group with Zariski open object, the whole group. So let's say partial compactifications of G, they will be this category of complex analytic space with the obvious morphisms. And of course, A is a subcategory of C. Of course, A is a subcategory of C. So we take these two categories. Again, quantum toric stacks will be stacks over A, will be stacks over A. So over this side. So what do I mean by a stack over the side? Well, in particular, I mean that there will be categories fiber in groupoids. So we're interested in categories fiber in groupoids over A. So we're interested in categories fiber in groupoids over A. Okay, so what is the shape? What is the structure, the basic formal structure of quantum toric stacks? Well, again, they are of the form X mod H, and they are categories fibered in groupoids over A. The objects are, well, these covers of T over T is an object in A. So I take an object in A, and it's a cover of T, an equivariant cover on ramified and analytic over T, and an equivariant map to X. Remember that X has an H action. Remember that X has an H action. So we need an equivariant map. Now, the morphisms of this category that will be the quantum toric stack, well, are obvious. What else could they be? They have the form of a comma category. And in any case, the lemma is that such things form a stack over A. Now, the motivation is that classical toric varieties are stacks over A in exactly this fashion. This is a reasonably easy exercise. So let's see how P1 is a stack over A. So P1, it becomes the category with objects, well, are, this is, I don't know why the AD, are pairs of T1 over C and T2 over C, such that T1 and T2 cover all of T. Well, I should have written here, sorry, again, M1 and M2. So the M1 of the intersection and M1 of the intersection is C star. And we have this descent condition that is just the glued map of the classical toric variety. And the morphisms are what you would think they are. Well, of course, it is a little bit funny to describe P1 as a category fibered in groupoids over A in this fashion, but this is what we need to do to describe rigorously the quantum toric examples. Already quantum P1 will be described in this fashion, and well, so P1, this is the simplest example. Well, so let's see how the quantum torus looks as a stack in this language. So the quantum torus, here it is, the quantum torus. Remember that there was a quantum lattice that produced a quantum torus. And what do I mean now by this symbol that I wrote in the introduction to this talk? Well, what I mean, it's a category fibered in groupoids over A. So what is an object of this category? Well, if I take any object of A that is affine toric varieties, well, it's a gamma cover of A, a gamma cover, remember, depends on gamma, and a M together with an M equivariant map, and the morphisms are these. So this is the way to describe the non-commutative torus or the quantum torus as a stack. And there is this construction, con functor, that will give me this algebra out of this. Well, or more general algebras with more generators, such as the ones that appear in the annals papers by Denis, Arro, and Orlov, and Ludmil Katzarkov. All these algebras and more appear out of this convolution construction applied to the stacks. Okay. So what is a morphism of quantum tori? Well, one can prove, after all the following track of all the formalism, that they are given by a linear map sending gamma to gamma. So we get, and I should have written here, sorry. I should have written here gamma prime, of course. So sending gamma to gamma prime, you have a linear map. It is the same of having one of these toric morphisms of quantum tori. So you can prove that. So let me give an example of toric morphism, because this will be very important for the construction of actual quantum toric varieties. So if I start with this quantum lattice inside of R, in the simplest case, I get this quantum lattice for h bar equals square root of 2. I start with this quantum lattice, just as before. This map actually makes sense here. It sends the lattice to the lattice. So this is to produce an endomorphism. So it sends the lattice to the lattice. And so this map actually makes sense when I descend in all this diagram to the quantum torus. This map makes sense. And this is written in the additive fashion before taking the exponential or taking the logarithm. But I can take the exponential and I can write this in a multiplicative fashion, and then the map looks like this. And so all I am saying is that this map, that would seem puzzling at first, makes sense for this stack. So this map from the torus to the torus, from the torus, real or complex, to the torus, to the quantum, from the quantum torus to the quantum torus, this map makes sense. And in the spirit of this theory, it is inside this theory, in the internal language of this theory, as we will see later on, we have applied tools from logic to carry out this theory further. In the internal language of this theory, this is an algebraic map. But let me just continue before saying anything like that. So let me give another example of an affine quantum toric stack. I'm ready to partially compactify the quantum torus to produce an affine quantum toric stack. So, well, you remember what is a quantum fan. And I'm going to take one of these cones to produce an affine quantum toric stack. Remember, it carries the information of gamma, a quantum fan. So what do? Well, I consider the case in which gamma contains these k elements of the canonical basis of RD, this k. There is more elements, of course, and gamma contains that. Imagine this cone here. Imagine this cone here. Imagine this cone here. So gamma contains V1 and V2. But of course, it contains more. And then, well, E gamma acts freely on TD. And so I can take CK cross TD minus K and divide by E gamma and produce this stack. This is the stack quotient that I described before. I mean, I could go on describing this forever, but I will start skipping this kind of description. But it is the category fibered in groupoids over A that has these objects. This is what this is. It's a category. These are, remember that T is an object in the category of affine toric varieties. So anyway, this is how we describe an affine quantum toric stack. This is what affine quantum toric stacks look like. They are stacks over A, and they, of course, by con, give a certain non-commutative algebra. Because the theory is so rigid, just as toric varieties tend to be, really the algebra recovers the stack and vice versa in this particular very, in all these toric examples. Anyway, let's now describe a simplicial quantum toric stack. Let's now describe a simplicial quantum toric stack associated to the, remember this is a quantum fan. A quantum fan has a fan plus gamma and the V's, the mark points on the rays. So now I'm ready to describe a simplicial quantum toric stack for a simplicial quantum fan associated to a simplicial quantum fan. I will not need, I will have an intrinsic definition later on of a simplicial or non-simplicial quantum toric. The non-simplicial case is being studied by, it has been developed and studied in the thesis of one of the students of Laurent Meersseman. I will restrict myself to the simplicial case in this talk, and in the paper is essentially the case that is described. Although, of course, the definitions work for the non-simplicial case. Not this one, though. This one, let's assume that it's a simplicial, we're in the simplicial fan situation. So we have the additional information. We have the fan, the classical fan, may be irrational. We have the mark points on the one skeleton of the fan. And we have the quantum lattice. No, I didn't mention it, but it should be obvious by now that the quantum lattice, unlike a classical lattice on RD, and this is all inside RD, unlike the classical lattice on RD, a quantum lattice is most often than not dense inside RD. In the irrational case, so to speak. Anyway, we take, let's take a maximal cone. You know, in one of these fans, let's take one of these maximal cones, indexed by I, just like in classical toric geometry. And then we get the map that straightens the cone, as expected, what you would expect. We take the map that straightens the cone, but of course, now this matrix could have irrational numbers. This matrix need not be rational, because this may be an irrational fan. This could be an irrational fan. So this matrix may not be rational. Nevertheless, we have that matrix. It straightens the cone. And then remember, this is the affine toric variety associated to that cone. And this is written in exponential form. And this is written in exponential form, in multiplicative form. And well, we have, it depends on this AI. And now, more generally, if we have a, well, any, you know, any cone there in the fan, well, now it's not a maximal cone, it's contained in a maximal cone. And anyway, we use the matrix of the maximal cone where it is contained to write this expression. And of course, this affine toric variety is inside this affine quantum toric stack. This quantum toric stack is inside this affine quantum toric stack. So we have this, and suppose that this one is contained here and here. This is two it's containing, this one is containing one maximal cone, but it's also contained in another maximal cone. Well, we can produce this co-cycle, and again, it doesn't need to be rational. This matrix is invertible. We multiply by this matrix. We produce this co-cycle that satisfies a co-cycle condition. And well, we have a collection of affine quantum toric varieties and the sent datum. Intuitively, that's enough to glue the quantum toric, the simplicial quantum toric variety. But, well, of course, we have to produce it as a stack over A with that datum, and we can do it. This starts to get quite technical. Let me just go very quickly over it. But we are going to glue all these along all these. We're going to glue all those affine toric varieties to produce a global quantum toric variety. Now, let me just stop before I do all this kind of very technical slide. And it's that this is just kind of the algorithmic definition given the fan. In the next talk, I will produce the quantum geometric invariant theory. The quantum geometric invariant theory is highly dependent on LBMB theory, and this is a beautiful, beautiful geometrical theory of certain foliations. And this will give an intrinsic definition of all these quantum toric varieties that won't be so algorithmic. It won't depend on the fan. On the contrary, given one of these, I can compute the fan. And of course, we will prove, I will not prove all the details, but I will state the theorem, that the category of quantum fans adequately defined, it's equivalent to the category of quantum toric stacks. In any case, we had all those Qs and the descent datum, and with them, I can produce a category fibered in groupoids over A that is moreover stack over A. And the objects of this category are these for every I maximal. So we have these objects for I maximal, and they satisfy a descent condition. Well, it's what you would expect, but you have to go through the technical details. And then you can prove that this is a good stack over A. I haven't talked about the morphisms. You can imagine the diagrams get a little bit dramatic. But, well, this is the one possible definition, the non-intrinsic, one possible definition given the fan of a quantum toric stack, gluing the affine toric varieties over the different maximal cones. Okay, so let's do an example. P1, of course. We take the classical fan for P1, and now we put a gamma, some gamma there that is probably dense in R1, and this depends on two numbers, a real number and a negative real number. Notice that the rank of this lattice can be arbitrarily large. Doesn't need to be 2 or 1, or can be arbitrarily large. I could get an arbitrarily large number of algebraically independent real numbers and produce an arbitrarily large rank gamma. In any case, well, here we have the quantum torus associated to gamma in multiplicative form. Here we have, well, exactly the same torus because it's just an automorphism, the minus sign in additive form. And here we have this gluing map, identifying this with this. And of course, here we have this one-side compactification of this quantum torus. And here we have this one-side compactification of this quantum torus. And there's many cases. It's very interesting. It's described in the paper. Let me just say, rather briefly, that when both of these numbers happen to be rational, and if I call Q the least common multiple of the denominators of A and B in minimal expression, and I assume that Q and QA are coprime, then I will recover classical weighted projective space of dimension 1. I will get this classical weighted projective space. And this is, in the shape of things to come, how you could start seeing that the rational points of the modular space are the classical weighted projective space. This will have, later on, next talk, I guess, because of time, this will have a modular space of these P1s for these combinatorics of the fan. Well, now we get the rank of the lattice or whatever. This will have a modular space, and this is how one could start seeing that the rational points of this modular space are the classical weighted projective lines. Okay, let me go to P2. So we have a quantum P2. And well, let me just say that using these linear algebra calculations by hand or by computer algebra, you could get these affine toric varieties, and you would get the gluings associated to the affine toric varieties to get a quantum P2. And you could get quantum P2, and you could later on also get the modular space of quantum P2s, given the combinatorics of this fan, and some rank of the lattice. So I'm running out of time. Again, when you want to study the rational case, you will get some weighted projective spaces. But the mapping to the classical weights, it's an extremely elaborate number theoretic mapping. And this also requires clarification and further investigation. It's an extremely interesting mapping. But let me just say before I finish in an incredibly fast way, that if I, rather than think of gamma, the quantum lattice, think of its generators, so to speak, this gives the difference between thinking of the quotient by the foliation and rather thinking of the quotient by the group action. This turns on the germ in terms of the classical physics in quantum field theory. And what we call a calibrated quantum fan. If I remember these kind of generators for the quantum lattice, including possibly virtual generators that do nothing. And then we have the following proposition, and the proposition is that the calibrated stack, this is the calibrated affine quantum toric varieties, and then we get a calibrated quantum toric stack. And the difference between the calibrated fan or the calibrated quantum toric stack and the one that I described in most of this talk is that this one is a germ over this with certain bands, abelian bands. So this is a germ over this with certain abelian band. If you want to think of it in terms of classical kind of like orbifold story here, or that kind of thing, or no, then this lives over this with a stabilizer at every point, z to the a. This is not an orbifold stabilizer, this is infinite, but kind of an orbifold stabilizer of every point here, z to the a gives this. But of course, there's a cocycle for this germ. So we have this calibrated quantum toric stack. And the modular space of calibrated quantum toric stack will be a nice the singularization of this other modular space, and that's also the reason why we introduce it. Anyway, that's all for today, obviously. Any questions? Hello, hello. Is anybody still there?
Well, it doesn't seem to be the case. So
Hello.
perhaps I have one question. What about the dual cones associated to quantum fans?
That's a bit of a problem. They will only make sense in the more elaborate theory that we are about to put out a paper, chimeric algebraic geometry. In this presentation of the theory, the dual cones don't make sense. But in the more elaborate presentation, in the version 2.0 of the theory, of this same theory, using these tools from logic, they do make sense. But they only make sense in a extension of the language of this theory.
Maybe another question that you mentioned earlier, that the fans could be polytopal. So the polytopes and the fans would live in the same lattice, in the same quantum lattice?
That's right. The polytope and the fan would live in the same quantum lattice. Again, we can do better than that in the chimeric theory. In the chimeric theory, gamma dual will make sense.
Okay, thank you.
Mm-hmm.
Hi, Ernesto.
Hello, how are you?
Hi, I'm good. Nice to hear you. Now, if we change the value of h from one irrational to another, do these things are these things isomorphic?
Not at all, not at all. Let me try to explain. Sometimes, but definitely not always. The modular space is more or less h bar modulo an equivalence relation. So h bar is the value. H bar, h here is I plus h bar. And h bar is the parameter, is the coordinate for the modular space. So next time I will describe the construction, the detailed construction of the modular space. But h bar is the parameter that parameterizes the modular space. So of course, for most instances of h bar, there will be non-isomorphic, but they will be in the same modular space. H bar is kind of the type Mueller parameter.
Oh. Okay, thank you. And when is the next talk? Is it next week or has it been scheduled?
Well, I guess it's next week, but you'll get an invitation by email. But again, before I finish my talk, remember, if you have any paper, anything you want to talk about in our seminar, please just send me an email and we'll set you up, and we'll continue running this IMSA seminar. So I'll email some of you to invite you specifically to speak, but just feel free to contact me. But because we're just, in this very unusual pandemic situation and we are learning how to do this, we decided to start with me to experiment the technology, and if there were no mishaps and everything, So I'll probably, so you don't feel any pressure next week, I'll probably speak next week, but feel free to contact me if you want to speak in 2-3 weeks, whatever, and about your own developments. But yeah, I think probably next talk will be next week. I'll have to ask the organizers.
Okay, thank you.
Yeah, perhaps I have another question. Well, if you don't have this duality of fans or of lattices, do you still expect to have some mirror symmetry picture?
Absolutely.
Okay.
Absolutely. There is a poor man's mirror symmetry picture here, but the richer picture, it's chimeric. We have to enrich this theory to the chimeric theory to do all that.
So it's again like taking dual some sort of battery.
That's right. And it will be, I'm guessing it will be totally compatible with the cluster situation that you have developed.
Okay. Thank you. Are there any other questions by the audience? It doesn't seem to be the case. So thank you very much, Ernesto, for this very nice talk.
Thank you all for connecting, and see you next time.
See you next time.
Bye-bye.
Bye.